So first demo I'm going to is a demo with the Raspberry Pi and a Geiger counter. So the setup here is a Raspberry Pi, of course, running the Wolfram Language. The Raspberry Pi is connected to a Geiger counter from SparkFun company, which is over here. And the communication happens over serial communication. So you do, I'll show you in a script real quick like how it works. But first I want to just kind of show you, since this is up and running, and I don't want to press my luck too much. So at the moment, it's using a scheduled task to basically count the number of hits that the Geiger counter has. And you can see this little green light here. That's the counter of the number of radioactive hits. So right now, I got this this watch that I got from Theo's Gray's Cabinet of Curiosities. A lot of scary things in there, but if I take if I take that away, then it just goes to 0, or sometimes there will be one blip, right? And so you can kind of see that the Geiger counter, it basically works. If I stick it right in front of there, and let me adjust, right? So now it's sitting right in front of this copper tube, which is actually doing the the counting. And I'll show you the script in just a second. Let me just do the other thing, which is much more radioactive. It's a piece of, I don't want to touch it for too long, but people ate from these things. It's called Fiestaware. And apparently this was a popular dish to eat from in the 1930s. So you could see that watch, it goes up to about 120 if you stick it really close. So let's see what this goes up to. Okay, so that goes to 251, as you can see, and it, the count. I'll just want to show you at least the script real quick, how this works. So real quick, you open a serial port with device open. In the case of a Raspberry Pi, the device name is USB 0. And you have to set the baud rate that the manufacturer specified here. Then device read buffer basically reads everything out of the buffer. You set you set T is 0 and the delta is 5 seconds. Print out the table, and then you run a scheduled task every 5 seconds, which is T delta, and then every 5 seconds you print out the current time and the count. So you do a device read buffer from the serial again. And you count the number of 49s, because that's the character code for 1, and that's how it comes. So that's where that number 49 comes from. Okay, I think I'm going to leave it at that. So because we got Ian coming up next, and he's going to do a demo with an Arduino and a force, like a Newton meter. What do you call it? What do you call it? A force sensor. Okay, good. All right, thank you.
Hello, everyone. My name is Ian Johnson, and I will be presenting how to use an Arduino and specifically a Vernier force sensor with the Wolfram Language in Mathematica. And so here is a live plot of a reading from this sensor as we manipulate it, basically. So as you can see, as we push and pull on the sensor, these readings are taken from the Arduino and they're put right in Mathematica for us. And so I'll quickly explain what an Arduino is. An Arduino is a small hobbyist electronics platform that you can use to hook up to all sorts of hardware devices. You can hook it up to motors, sensors, LEDs, all sorts of physical hardware things. And so now, using my drivers, you can use all of the physical hardware world that is the Arduino. You can use that all within Mathematica, and I think it's pretty cool. One of the cool things about the Arduino is that it's an open source platform, and so there's lots and lots of work that lots and lots of people have done on on building various shields, like, for example, we're using the SparkFun Vernier interface shield here. You can get lots of other shields that people have built, and there are libraries written for these shields that people have. There's a lot of work that has been put into various things for this. So what's powering my Arduino driver is what's called the device framework. The device framework is a new feature to Mathematica 10. It's basically a standardized set of commands like device open, device read, device configure, etc. That can be used with many, many devices, and specifically here we're using it with the Arduino. And so here I'm going to read from the Vernier Arduino object, and so that's the voltage on analog pin 0, and that's the digital state of pin 2. And here I can go and I can write a value of 1 to turn the LED on, and I can write a value of 0 to turn it off. Yep. And so we can do other cool things. Here's a vertical gauge of the force sensor. You can see that. So there are lots of, once you get this data into Mathematica, you can do all sorts of things like it. One cool device framework function here is the device read time series. And so for the next 2 seconds, it'll take data readings, and we can go and we can plot that, or well, this is kind of boring in straight line because nothing moved in 2 seconds. But all of the cool time series functions that you can actually use this with live data that you collect right inside Mathematica. And so another cool thing about my driver firmware is that with this device configure, you can configure the Arduino to have various functions that you write yourself, like custom functions written in C or C++. You can upload those to the Arduino. Turn that off quick, and then I'll upload that. And so what this basically enables you to do is write any kind of Arduino function. Here we're going to blink an LED, but you can obviously do much more complicated hardware things. Upload that will be on the Arduino, and now with device execute, we can now execute that device. So as you can hopefully see, the little blue LED flashes for a very, very short amount of time. So a future feature of this will be the translation of Wolfram language code into Arduino code, so you'll be able to write these functions in the Wolfram language to be uploaded to Arduino. So as I was saying before, there are lots and lots of work that have been put into building these libraries and these shields for the Arduino. And so, for example, there's the servo library for controlling servos, or here's a handwritten library that I wrote myself that blinks an LED for Morse code, or here's the Vernier library. But you can upload all of these libraries to be used with the Arduino. So what this basically allows you to do is, if you have a shield or hardware device, it's very easy to plug it into the Arduino, and then in Mathematica you can write up a quick little driver that uses that library to interface with it. So here what I've done is I've written a SparkFun Vernier interface shield driver. And so I've already opened the driver, so I don't need to do that. But so we can read here, and so what's really cool about this specific driver is with Vernier sensors, the Arduino can pull the sensor to actually see what kind of sensor is attached. So here we can see this is a dual range force sensor, which is on the 50 Newton calibration range, and we can see it has units of newtons as reported by the sensor. We can see what the calibration data is, the calibration equation type, the intercept, blah blah blah. All of that is automatically gotten from the sensor, and so if I were to plug in a different sensor, all of this would change, and all of the device read options would change to reflect that. So here we're going to push on the sensor really hard to show that it maxes out at about 50 newtons. So there you can see, I guess it goes up to 60 newtons, but so you can see if we were to change it to 10, it would change to 10 newtons basically as maximum. There we can see the units, or so it's really cool because it uses calibration data to determine the units for us, and so we can use all of the units functions in Mathematica. So for example, if we want to convert that to pounds, here's almost 0 newtons in pounds, but it has all these units built into it, and so it's really useful for stuff like science experiments because units are built right into it. And so what we're going to do last is we're going to calculate the coefficient of friction between the new kind of science book and a table. Okay, so what we're basically going to do is we'll read from the sensor using device read time series as we very slowly increase the force with which we pull on the book. So for the next 20 seconds, it will be gathering data basically as we pull on it, and the maximum of that will be the maximum friction force that's given off, and that we'll use that to calculate the coefficient of friction. So once that quick finishes here, we'll do a list line plot of that and have a quick look at the data. Okay, so here. So we can see, well, it kind of goes off the screen here. I'm not sure why list line plot isn't working, but maybe if I go
you want to do
plot range to all maybe. Yep, there we go. So we can see it maxes out around, oh, that looks like about 10 newtons. But let's calculate what the actual maximum is. So if you take the max of the force data, I guess it's 9.85 newtons is the maximum. So now what we're going to do is now we're going to measure how much it weighs. And so we'll pick up the book very carefully, obviously, and we'll reevaluate this to measure how much it weighs. So as we measure that, as soon as this finishes evaluating, but the maximum there will basically be the weight of the book in newtons. And if we remember correctly, the coefficient of friction is defined as the ratio between the maximum friction force and the normal force, basically. So the normal force is going to be equal to the weight, so we can take the max of this again. And so here's our normal force, that's 25 newtons, and here's our resistance force, this 9.85 newtons. So we'll divide those two, and we get 0.32 as our coefficient of friction. So thank you very much.
Hi, my name is Tom Sherlock. I work here at Wolfram Research, and in addition to working in the user interface department, I also, in my copious spare time, I like to do astronomy when I get the chance. And so, of course, one of the things that I've been doing is seeing how Mathematica can make my astronomy hobby even easier and more rewarding. And one of the great things about Mathematica, in addition to being a powerful computational tool, is it has a lot of data built into it. And that was one of the things that we're promoting in these later versions of Mathematica. One of the things that Mathematica has in particular is astronomical data. And you can easily access this and make use of it. So thinking about that and thinking that I like to run my telescope, I used the recently introduced serial connectivity package in Mathematica 10 to write a telescope control package. And the telescope control package will run on any version of Mathematica because all it requires is a serial port. For instance, it will run on the version of Mathematica that's running on this Raspberry Pi here, which I have plugged into the back of my telescope. So by doing that and having Mathematica look up the coordinates of different astronomical objects, I can have it set my telescope mount to point to those objects and start tracking them. What I'm going to do is I'm going to have Mathematica look up several different astronomical objects, and then the scope will slew to that, and then you could either observe or take pictures. So the first thing I'm going to do is, right now the scope is in the park position, which is kind of a neutral position, but I'm going to have it slew to the Great Cluster in Hercules. And it's what it's doing right now is it's looking up the coordinates for M13, which is the Great Cluster in Hercules, and it's transmitting them to the mount controller. So now the scope is pointed at M13 in Hercules. So now I'm going to, so let's say I've taken some pictures or observed it for a while. Now I'm going to point it at the Ring Nebula. So it's looking up the coordinates of that, and it's sending them to the telescope device. Okay, and now I'm going to point it to M56. And it's looking up the coordinates for that. And it's a little lower object right now. Of course, this is during the daytime, so it's not going to be easy to observe them. And finally, I'm going to do M10. And the pause you're observing is it's looking up the data for this, and then it's transmitting it to the telescope. There's basically two different types of telescope protocols that are widely in use today. There's the LX200 protocol and the Nexstar protocol. And the package I've written will use both of those protocols to control almost all of the consumer-grade telescopes and telescope mounts that are sold today. Then when you're done, you can tell Mathematica to put the scope back into the park position. And there it goes. So that would be a complete observing session. And you could program it to automatically go through a sequence of objects. For instance, one of the things you might want to do with this sort of control would be to programmatically look for supernovas in a bunch of different galaxies. So you could set up your Mathematica package to have a list of galaxies that may or may not have supernovas in them. And then through the course of the night, it would go to any one of the galaxies in the sequence. It would take a picture and then proceed to the next galaxy. And then you could use image processing techniques to see if there's a new star in that galaxy. People automate supernova hunts this way all the time, but this is one way you could do it with Mathematica. Now, tomorrow, we're going to actually take this setup out into the field, as it were, and try to get some pictures of the moon or something like that. So when I see you again, we'll be back in the field. On the U of I campus, you can see me setting up the telescope. I'm inserting the Pi cam into the telescope's eyepiece holder. There I'm connecting the serial cable to control the mount, and there the Pi cam is instructing the telescope to point towards the moon. This is all running in Mathematica on the Pi cam. There you can see it's pointing at the moon, and here you can see it's just captured an image of the moon. You can see the craters down there in the lower right-hand and upper right-hand corners. And there you go.